In this video, we're going to be looking at the concept of vectors and scalars and how to add and subtract vectors with some basic applications of them. What we're going to do, we're going to introduce the concept of scalars and vector values. We're going to define the term resultant. We'll identify variables for scalars and vectors. We'll also identify and find opposite vector values. We're also going to learn how to add and subtract vectors in a graphical format. Why are we doing this? Because vector values make up the majority of values that we are going to work with in the physical world. It's impossible to work with almost anything dealing with physics or engineering without a vector. So here we have a guy with a treasure chest, and we're going to take the treasure chest, hide it from him, and then give him a clue on where it is. And we'll see if he can figure out in one guess. The hint that the guy is giving us that is hidden 100 yards from where he is. Now the question is, where is it? Can he find it in one guess? And the truth is, most likely not. The reason is, while there is a distance that we're given, there wasn't enough information to know the exact location. If we have it buried somewhere around, it'd be a circle from where he is. Anywhere on that circumference is the treasure chest, but we don't know exactly where it is. So the information that we gave him, the distance that it was away, was known as a scalar. These are magnitudes or just an amount, mostly the values that you've been working with in most of your math classes. Scalar values are incredibly important. They tell us how big something is, or how small, how much, how many, how fast, how slow, how strong, or how long something is. Just a straight up magnitude or amount. And the term magnitude just simply means an amount. Whenever we add or subtract vectors, we always get a result. These are the classic things like I have 5 boxes and then you give me 3 more boxes, so now how many boxes do I have? The result is simply just adding up those two numbers. So if we go back to this question of how can he find the treasure, what other information is needed? And instinctually we all know that it has to be a direction. If we were to turn around and say that the treasure box was 100 yards away, 30 degrees north from the west, you'd be able to find it very quickly. Because all you have to do then is look out in the west direction and then tilt 30 degrees north from that west. And now I know exactly where that treasure box will be since it's 100 yards away. This value that we just gave is called a vector. Vectors are anything that have both a size, aka magnitude, and a direction. If you saw the movie Despicable Me, that was the thing that made vector. Vector was, he always pointed out that he had a magnitude and a direction. You can actually think of a scalar as part of a vector, because a scalar is a magnitude, and a vector would be a magnitude or scalar with a direction. Vectors answer the exact same questions that scalars do, but give us even more information, such as where something is going to be going. Whenever we add or subtract vectors, we don't get a result, we get something called a resultant. The big distinction between a result and a resultant is a resultant will give you a direction as well as a magnitude, while the result gives you only that magnitude or an amount. So here we have some examples of scalars versus vectors. Whenever we talk about just a distance, the amount of kilograms something is, how much charge is involved, not talking positive or negative, just how many coulombs there are, how fast something is moving, the amount of energy something has, a magnitude of force, the magnitude of acceleration, magnitude of torque, magnitude of momentum. These are all examples of scalars, everything that has a magnitude but no direction. Vectors, however, are far more selective. They have to have a direction as well as a magnitude. So instead of a distance, we have something called a displacement. And we'll talk more about that throughout the year. Instead of speed, we have velocity. And they are very different, speed and velocity. Velocities always have a direction. A true acceleration, the true value of acceleration, I should say, has a direction, as well as forces, torques, and momentums. So anything that has a direction involved with an amount will always be a vector. So let's take a look at how we add scalars. The way that we often look at it is we have different amounts and we just simply place them together. So if I had 3 plus 2, I could turn around and have 3 dots, 2 dots, and say, how many dots do we have? We could say, oh, there are 5 dots. And we say, okay, well, what happens if we have 2 plus 3? We see we have 2 dots, and then we have 3 dots. We count them all up. We still get 5 dots. So the order in which we add scalars doesn't matter. And all we're doing is we're just counting up the amount of items that we have. Now, when we subtract, we can think of it as taking away. So here I have 3 dots, but then I'm going to have these holes that are going to take away 2 dots. And so I have 1 dot left. But let's say I have 2 dots, and I'm going to go 2 minus 3. Well, then I have 2 dots, and I have 3 holes, and each hole is going to eat up a dot, but in the end I have 1 hole left over. So now I have -1. And we learn very quickly that when we're subtracting, the order matters. With addition, 3 plus 2, 2 plus 3 always gives you the same value. But when we have scalars and we subtract them, we always come up with opposite values. Instead of 3 minus 2 equaling 1, I get 2 minus 3, which is -1, because I have less than a dot. I have a hole that's going to eat a dot as soon as I get one. Back in math, we introduced the concept of integers with something like this, where all the positive numbers are on the right side of the 0, all the negative numbers are on the other side of 0. So I could turn around and say in a problem like this, I could say 2 plus -3, and then I could see exactly where that lies on my number line, and I could see that would end up on a -1. So now all of a sudden we have magnitudes and directions. The magnitude's how far away you from 0, and the direction, positive being on the right side, negative being on the left. So this actually lays down the foundation for vectors. And if I was to take a look at the math problem of +3 plus +2, we would learn, or you learned earlier on, that you could just draw a line, or an arrow I should say, from 0 to 3 being 3 units long, and then that would represent +3. Then I could draw another vector, or another arrow I should say, starting at 3, that would be 2 long, going in the right direction since I have a +2. And this ends on +5. So the answer to +3 plus +2 is +5. And I could see that if I reverse the order, I still end at +5. So once again, the order doesn't really matter when I'm adding integers. But the truth is, while we're adding integers here, we're doing more than just that. I have 3 to the right, which is a magnitude with a direction. I have 2 to the right, that's a magnitude and direction. So I'm also really adding 2 vectors. And the resultant of these 2 vectors is 5 to the right, or +5. And again, if I go 2 to the right plus 3 to the right, I end up with 5 to the right. One of the things that was very confusing with people with subtraction with integers is you seem to just change the sign of the second number and then add. And that's because subtraction doesn't really exist. It's really the adding of the opposite. Whenever we say subtract, we actually mean add the opposite of the thing we're talking about. So instead of this really being 3 minus +2, it really is +3 plus the opposite of +2, which is -2. So if +2 is going to the right, -2 is going to the left. So I would draw out my integer vector from 0 to 3 going to the right. Then at the very end, at 3, I would draw a 2 now going to the left. And now I end at 1 to the right, or +1. If I reverse the order, though, I now have +2 minus +3, which is really just adding the opposite of +3, which is -3. So I would start at 0, going 2 to the right, and then at 2, I would go 3 to the left, because it's -3. I now end at -1. So I can see again that I end up with opposite values when I subtract integers when I switch their order. Now, as I had said a little bit earlier on, that I can, when I'm adding the integers, I really am adding vectors when I'm doing this little arrows on the number line thing. And that's exactly how we add vectors. Since vectors represent anything that has both a magnitude and a direction, we always draw vectors out as not little dots or holes, but as arrows. The length of the arrow represents how big the arrow is, how big the vector is. And the direction that the arrow points in is, of course, the direction that the vector is pointing in. Here we have two vectors. We have vector A, which points 3 to the right, 3 meters to the right, and vector B that points 6 meters to the right. And if you notice, vector B is in fact twice as long as vector A, and that's because it's twice the distance. Whenever we draw out our variables to represent a vector, just like we do in math with x equals 3, we're going to use special symbols to illustrate that it's a vector versus a scalar. We're still going to use letters, just like before. The letters are the classic variables that we use. But to show that they are vectors that have both a magnitude as well as and a direction instead of just a magnitude like the regular everyday values that we use, or variables that we use, we're going to put a little extra on the variable. So sometimes you'll have a regular print with an arrow up on top to show that it's a vector. Sometimes we'll have it in a bold print. Either way, those represent vectors. When you see an everyday regular print variable, that means it's a scalar value, the kind you often see in your algebra classes. So again, if you're bolded or have an arrow up on top, you're a vector. And if you are just a regular everyday letter with nothing special added to it, then you're going to be a scalar. Vectors have opposites just like any other number. They're always going to cancel out. The definition of an opposite is that it nullifies you out completely, bringing you to 0. So if vector A was 3 to the right, what vector would bring me to 0? And that would be 3 to the left. An opposite vector is always the same magnitude, but always 180 degrees in the opposite direction. So if I had a vector that was this long, going to the left, that would be negative A. And since I cannot draw out in bold, I put the little arrowhead. Please notice that when I did the type, I was able to use a bold letter A. Here I have 4 pounds going along the positive y-axis. What would bring this? That would be 4 pounds in the exact opposite direction. So that'd be along the negative y-axis. This one's a little bit trickier. Here I have 12 meters per second at 60 degrees south of east. In other words, south from the east. So if I was looking in the eastward direction and I went south 60 degrees, that's where I'd be going. What vector is going to cancel this out? Well, it would have to be going in the exact opposite direction and be exactly as long. So this would have to be then 12 meters per second, and it would actually have to be 60 degrees from this axis. Well, this is my west direction, if this was east, and this is in the north direction. So this would actually be 12 meters per second at 60 degrees north from the west. Please notice, the south just switches to north, east just switches to west. That's how I get my exact opposite. The magnitude of the angle and the magnitude of the vector length itself don't change at all. I'm doing nothing with those things. I'm only changing my exact axes and references. East becomes west, 180 degrees apart from each other. South becomes north, again 180 degrees apart from each other. When I add vectors, I'm really just going to be drawing out arrows, one right after the other. We call this the tip-tail method. The first thing we're going to have to do for our diagrams to make any sense is to have a scale. This is a proportion that all vectors will be drawn to for our problem. Every problem can have a different scale, but you cannot use different scales within the same problem. You're going to create an origin to draw your very first vector, and you're going to simply draw out that vector to scale. Then at the very tip of that vector, you're going to create a new origin for your second vector to be drawn. Then you're going to draw that second vector at the exact same scale you drew the first vector. And then you just keep doing this over and over and over again until you're all out of your vectors. Then you're finally going to draw your resultant vector. This is the answer. It starts from the very beginning of the problem, which is the start of your first vector. It is drawn to the tip of your very last vector, which is the end of your entire problem. Then using your ruler and protractor, you can measure out the length of the vector and the angle. By using your scale, you can convert your length back into whatever it's going to represent in terms of its magnitude, and you can use the protractor to give you the angle and direction that the vector is going to point in. So, for example, we're going to go through a couple of quick problems with this. I have vector A, which is 60 meters along the positive x-axis, and vector B, which is 30 meters along the negative y-axis. And I want to simply add vectors A and B together. So if you notice, I have an origin already pre-drawn here in the middle of my grid. And the first thing I'm going to do is I'm going to set up a scale. You can see that right here. I'm saying 1 centimeter equals 10 meters. It could be anything I want. I like that one as my scale. So I'm going to use my ruler, starting at my origin. I'm going to draw out my first vector, which would be 60 meters, which is 6 centimeters, because 60 divided by 10 is 6. At the very tip of this vector, I'm now going to create an origin for my second vector. And then once I do that, I will draw out my next vector. So here I have my second origin, and I now draw out a vector that is going to be 30 meters, so that is 3 centimeters long. I'm now out of vectors. If I had a third vector at the very tip of the vector here, I would simply draw out another origin and draw out my next vector to scale. But since I'm done, I'm simply going to now draw a vector from the start of my first vector to the finish of my last vector. So I draw out from start to finish. So again, here's the very start of my problem. Here's the very finish of the last vector. And I can measure this out and see that it's about 6.5-ish centimeters. And I can use my protractor to measure the angle. To do this, you simply line up the protractor with your axis. Make sure the little dot is on the point where the vector is starting, and you can simply measure this out and see that this is somewhere between 25-ish, about 25-ish degrees, which would be below the positive x-axis, because here's my positive x-axis, and I'm going about 25 degrees below that. So I can say that my resultant is 65 meters at 25 degrees below the positive x-axis. Now this is actually all an estimate. It's a pretty close estimate, but it's not exactly precise. If I wanted to be truly precise, I'd have to use trigonometry. But right now we're just doing a simple graphing method. So close enough. So this is close enough to what we're looking for. Here we have another situation where we have 3 vector forces acting on a box. Please notice these vectors are not drawn tip to tail. The first mistake people do when they work with this is they start doing weird connections with the tips and they can't find anything. That's because these vectors aren't drawn out properly. It's fine for a diagram for the problem. I can see all the forces acting on this block. but not how we're going to add them. Now, one of the things that people also get confused on is, which vector do I add first? It doesn't really matter. The order of addition does not affect the outcome. So you can pick whatever vector you want to do first to add. But the first thing we need to do is, of course, come up with a scale that we're going to use throughout the entire problem and create an origin. So I'm going to pick what 1 centimeter equals 10 newtons. Newtons is a force, not a distance, but that's okay because it's just a representation of those magnitudes. So it's going to be at just fine. I have my ruler and my protractor, so I'm now going to start with an origin and draw one vector to scale. So down below here, I now have my origin, and I'm picking not the center of my paper because I can see all three vectors are in the upward direction. So some good strategy, pick near the bottom. I'm now going to draw out my very first vector, and I'm picking the one that's off to the right because it's just off to the right, and I can go in a circular path around each one. Since it's at 50 degrees above the positive x-axis, the trick that you can do is draw out a thin line that is 50 degrees using your protractor. Now this line is way too long, but I'm not actually going to use this line for my vector. I'm going to simply measure along the line and then draw out my vector off of that. So using my ruler, I now measure a vector that is 3 centimeters long because 30 newtons divided by 10 newtons is 3 centimeters using my conversion factor that we had selected earlier on. Now I'm going to draw out a new origin for my second vector. That is going to be at the tip of the first vector I just drew. This guy is now 20 newtons going straight up. So I'm going to need to now draw out a vector that's going to be 2 centimeters long, which I simply do, and you can see that my measurement right there for 2 centimeters. I'm not done, I have a third vector. So I'm going to draw out a new origin at the tip of that second vector, and then I'm going to now measure out an angle that's 30 degrees. Oh, sorry, that's going to be 60 degrees to the right of the positive y-axis because that's where the 60 degrees is coming from. It's coming from the y-axis. It's going to go out left 60 degrees. So I'm going to use my protractor, measure that out. This way it's not some random guess. And now I will measure out a line that, or I should say a vector, that's 3 centimeters long. Because again, 3 centimeters is the same as 30 newtons. I now have all my vectors done, so I can now go from start to finish to find out my resultant. Now I can simply use my ruler to measure its length. And simply using the ruler, I can see that's approximately 6 centimeters, so that's going to be 60 newtons. And then by laying my protractor on the x-axis, I can now measure the angle. And I can either measure from the negative x-axis or the positive x-axis. Normally you get a choice. If not, use whatever axis they're telling you to use. And I can see that measuring from the positive x-axis, which is right over here, that's 98 degrees going all the way around. So that's going to be 98 degrees above the positive x-axis. Or if I'm above start referencing the negative x-axis, I see that's only 82 degrees. So 82 degrees above the negative x-axis. Both answers are correct. I just have to pick whichever one I'm most comfortable with. So here are some examples of any of the acceptable answers that we can come up with. We got 60 newtons at 98 degrees above the positive x-axis. We have 60 newtons at 82 degrees above the negative x-axis. We can even just use our protractors on the y-axis and measure that this is only 8 degrees. So I could use that if I wanted to. Or I could even go with the negative y-axis and measure out the angle from there. This is why, when giving an answer, you must always state what your reference is. because you have ultimate freedom in which reference to use. So you need to be clear on what reference you're choosing to use. If I want to subtract vectors, I'm going to do the same thing that I did with integers. You never subtract. You simply add opposites. So let's say I wanted to have the vectors A is 60 degrees along the positive x-axis, B is 30 degrees along the negative y-axis, and I want to do A minus B. Well, I can't. No such thing as subtraction. So what I can do is A plus negative B, or A plus the opposite of B. Now, when you say that, that's going to make a lot more sense, because if B is 30 meters along the negative y-axis, then the opposite of B would be 30 along the positive y-axis. It's a little bit more instinctual. So, just like before, I'm going to have my origin, and I'm going to draw out my vector 6 centimeters long, going to the right on the positive y-axis, because that is my vector. So again, you can see my scale. You can see that I'm going to be using my ruler to measure my length, and I can see that it's 6 centimeters long. And now at the tip of this vector, I will now simply draw out an origin and draw out a new vector. And again, it will be 3 centimeters long. But please notice, B was supposed to go along the negative y-axis. This is the opposite. The opposite of 3 along negative y is 3 along the positive y. Or I'm looking at my magnitudes here. Another vector, I should say 30 along the negative y. The opposite is 30 along the positive y. I now can draw out my resultant from start to finish. I can measure out this length, and I can see that it's about 6.5 centimeters, so about 65 centimeters, just like last time. And I can measure the angle, which is still about 25 degrees, but above the positive x-axis. Does the problem A minus B equal B minus A? Well, for this one, I'm going to have to subtract out the vectors in the order that they're given. So right over here, I have A minus B, exactly as it was shown before. But if I want to do B minus A, I would actually have to draw out my vectors in this particular order. This is no longer going to be, this one, I should say, really is B plus the opposite of A. So B was really 3 along the negative y-axis, and A was really 6 along the positive x, so this would be 6 along the negative x. So if I draw this out here, this would be what the opposite of what A is, drawing that at the tip of B. And I can now draw out my resultant, which would be going off right over here. Please notice these vectors are 180 degrees off of each other. Not only that, but if I overlap them, I see these two vectors cancel out. That means my answers are the exact opposites of one another. Whenever we add vectors or values, the order doesn't matter, just like with scalars. That's because the ability to have the order not matter when you add isn't about the type of number, it's about the process of addition. Switching the numbers that you subtract or switching the values that you subtract always give you an opposite answer. This isn't a thing about scalars or vectors, that's a thing about subtraction. You always get the opposite result when you switch the values that you're subtracting. All right, that's going to wrap up this video. I hope it makes some sense. Be sure to come into class tomorrow with questions on this, because we're going to just do some practice work on this. It's not complicated. It just takes a little bit of practice and a ruler and a protractor. So if you don't have a protractor, you definitely want to go get one. Don't buy anything expensive. Cheap ones work just as well.